All right, welcome to our lesson on Hooke's Law today. So what is your goal, or what do I expect you to be able to do? I expect you to be able to explain Hooke's Law, and I want you to be able to apply it to some real-world situations. So you can see that there's a bit of a trend in our goals, and it's being able to make sure you can make a direct connection with the daily concept and the associated real-world problems here. So the force exerted by an elastic device, so we could be talking about a spring, could be talking about a bungee cord, could be talking about a rubber elastic, is proportional to the distance the spring has moved, and I use the spring as a generic term throughout the unit, how far it's moved from its equilibrium position. So let's talk about equilibrium versus your compressed / stretched locations here. So for a spring, if it has no force, we call equilibrium right there. So that's our equilibrium. We call that the natural rest position. Natural rest position. So if there's nothing acting upon it, then that's what it'll look like, or what the spring will, the nature of the spring. Whereas if we stretch or compress, so I'll do double diagram here. So this is a spring that someone is pulling on, and then we have someone pushing on it. So here we have what we call the stretch. So it's being extended out as far as it can, whereas this is what we would call a compression. And the end point is some distance away from that equilibrium. So equilibrium is where the spring would like to exist. Stretch or a compression is what we're looking at in terms of the forces acting on it. Now, when we do that stretch or compression, the distance that it is from that equilibrium is going to be our measurement of delta x. So delta x is a measurement of how far is the spring being moved, stretched, or compressed from its natural rest position. So there's our delta x. So moving along here, so for the ideal spring, Robert Hooke, he did some research, and he found that the relationship was that the force placed on an object, or force placed on a spring or a elastic material, is equal to negative kx. So F of x, that's what we call our elastic force, okay, or force contained in a spring. Force contained in an elastic device. K is what we call the spring constant. So every spring, every bungee cord, every elastic band has a different property, and that spring constant is what gives it that individuality. It's how compressible it is, and we'll talk about how it's developed in a second here. And finally, x, or it should be actually delta x, is displacement from equilibrium, as shown in the diagram above. Displacement from equilibrium. All right. So the last part here down below, if x is greater than 0, so if we stretch the spring, then f of x is going to be a negative number. All right, so the spring force will be a negative number. Whereas if we compress it, it'll be a positive number. So it goes toward, it's a sign convention. So that negative number, we always say negative numbers is stored energy. So that spring will, in a stretched spring, will have a negative amount of energy, wants to pull back, whereas a compressed spring wants to push away. So there's your negative and positive. You'll find the sign convention, as long as you're consistent and think it out, the sign convention is not going to be a major issue as you do some of the problems. So let's take a quick look at the analysis of Hooke's law. And I've seen some of this when I did some material analysis courses in university. We do look at this because a lot of materials follow this property. It doesn't necessarily have to be a springing material, okay, like your traditional spring that you're visualizing. It could be a piece of steel, a piece of metal, or a piece of plastic that follows these similar characteristics or properties. So kind of neat when you actually get a chance to see it in action here. So what happens when we stretch an object? This on the y-axis is going to be a measurement of the force that's applied, and then on the bottom is going to be our delta x, so that is the stretch factor. What you'll find with elastic materials, so metals, plastics, and so on and so forth, is that there'll be a linear component. So the material will result in a linear component like that, and then once we reach a particular point, the graph goes like that. Why is that? Well, since you're not here to throw out ideas, I'll just go ahead and tell you. In this linear part, this is what we call the elastic region, which means that if you stretch a slinky, it will return back to its natural form. If you stretch an elastic band, it will return back to its natural form. The inelastic region is where we start to deform the material. So basically this is unslinking a slinky or snapping an elastic band in half. So in that elastic region, what happens is we end up with failure of the material. All right, it will not return to its original state. So it's been unslinkied, it's been stretched and broken. It's to the point where it will not return to its natural position. What we're more interested in this course is that elastic region. So the elastic region has a linear relationship. And you get an opportunity, if you haven't already, to do a lab where you get to actually see that relationship exist. So what is actually involved here? Well, because it's a linear relationship, we can calculate or determine the slope of a line. Slope is delta y over delta x. That delta y is the change in force with, actually it's going to stay as delta x, is expansion there. Rearranging it, we find that change in force is equal to m delta x. And that is where Hooke develops his law. Force of a spring is equal to, he changes the letter m to the k to indicate we're dealing with a spring constant, delta x, and he places a negative in there. I'm going to address the negative a little bit later on as to why the negative is there. All right. Or actually, I can really do it now. Before I go any further, the units, before I forget, in this case, we are going to have your K is newtons per meter. Newtons per meter. So how many newtons does it take to stretch it 1 meter? Now let's talk about why he put the negative in. In the scenario over here, we are stretching the spring. This is a model where we're actually stretching the material. Delta x is increasing, so delta x is increasing, so we are stretching the spring. On the previous slide, I noted that if you stretch it, the force will be a negative value. Okay, so he's just aligning, or maybe we align it based on his formula. That's why that is a negative k delta x. If it's a compression, delta x would be a negative value, which would make it a positive force, so you know it's a compression. So that is where those positive negatives play a role here. Okay, so an example. Student stretches a spring horizontally a distance of 15 millimeters. So of course we are working SI standard here. So we need to convert that 15 millimeters. So delta x equals 0 point, and we need to move that over to read 0 point. Oops, keep putting 0 point. Putting my mental brain cramp here. 0.15 meters. We've applied a force, and because it's a spring, we know it's Fx, and it's 0.18 newtons and east. So a part is, what is the force constant for this spring? So force constant is a fancy term for the value of K. This is our force constant. So for A part, f of x equals negative K delta x. So we are stretching the spring, so it would be a negative 0.18, negative K times 0.015. My spring constant then, my K value is 12 newtons for each meter. All right, so therefore, spring constant is 12 newtons per meter. Now, question B, what is the force that the spring exerts on you? So if the student is pulling that spring outward, how much force are you feeling? This is just related back to some of the stuff we talked in earlier units and in the 3U course. This is Newton's third law. So if you were applying a force, if FA is 0.18 newtons, then the reaction force, FR, is going to be equal in magnitude but opposite in direction. So it's actually going to be west. So it's just a Newton's third law. Okay, just threw it in there as an afterthought as I was doing the question. And a good thing, it kind of ties things together, that for a reaction there's an equal and opposite reaction. All right, so now what I'm going to do, I'm going to break it off here. I'm gonna need a second video anyway to finish up the material that's remaining. So I'll end it here and we'll pick it up and finish in the next video.